Okay, so in the previous lecture we have just started with tie line frequency bias control. So here also starting from the same point, that equation 38 and 39 it suggests that there will be steady state error of frequency deviation and tie power deviation following a change in load, that is load disturbance, right, either increase or decrease in load, and that is equation 38 and 39. The steady state values of both frequency and tie power deviations are given, right. So, to correct those steady state errors, supplementary control must be given in both the areas. I mean, our objective is to bring this steady state error to 0, for which we need that supplementary control action, right. So, the supplementary control in a given area should ideally correct only for changes in that area, right. In other words, if there is a change in area 1 load, there should be supplementary control action only in area 1 and not in area 2. So, that equation 38 and 39, equation 38 for your frequency steady state error and this is for tie power deviation steady state error, indicate that a control signal made of tie line flow deviation added to frequency deviation weighted by a bias factor would accomplish the desired objective. This control signal actually is known as area control error. So, suppose you have a two area system, that is we have seen, suppose if suppose a load disturbance has happened in area 1, then area 1 supplementary controller it should respond, right, and it should accommodate these load changes, and area 2 supplementary control should not respond to this, but it during your dynamic your transient period, that it will act, but at the steady state, that if any load changes occur in area 1, that area 1 generation must accommodate that, right, and there should not be at steady state there should not be any power is generated by the generators of area 2. That means, at steady state generation of area 2 will be 0, because there is no load disturbance in area 2, right. So, the area control error for area 1 and area 2 can be defined as generally ACE1, that is area control error of area 1 is B1 delta F1 plus delta P tie 1 2, this is equation 40, and ACE2 is equal to B2 delta F2 plus A1 to delta P tie 1 2, this is equation 41. Now, we define say B1 is equal to beta 1 is equal to D1 plus 1 upon R1, and B2 is equal to beta 2 is equal to D2 plus 1 upon R2. So, beta 1 and beta 2 basically are the frequency response characteristic of area 1 area 2 respectively. In general, we call this is area frequency response characteristic. So, integral control law both for area 1 and area 2 are given by that u1 will be minus ki1 integral of ac1 dt and u2 will be minus your ki2 ac1 ac2 dt, right. So, it is actually later we will see that you have your this is your input say for area 1 ac1, right, and this is your that integral gain ki1 upon s, and this is my u1, right. Therefore, u1 is equal to minus ki1 upon s ace1, right. That means, its integration actually u1 will be minus ki1 integral of ac1 dt, right. So, that is why this u1 is written as minus ki1 integral of ac1 dt, this is equation 43 for area 1, and u2 is equal to minus ki2 integral of ac2 dt, this is equation 44, where ki1 and ki2 are the integral gain settings for area 1 and 2 respectively, right. So, these gains integral gains actually need to be optimized at the of course, for the classroom purpose we cannot optimize through simulation, but I will tell you how to optimize such things, right. Now, next is basis for selection of bias factor, right. That means, this B1 and B2 selection for this one, right, that is bias factor B1 and B2, that is called frequency bias, right. So from the point of view of steady state performance, the selection of bias factor is not important, right. Any combination of area control errors containing components of tie line power deviation and frequency deviation will result in steady state restoration of the tie flow and frequency, since the integral control action ensures that AC is reduced to 0. That means you take, I mean, for example, suppose we are overwriting it, I hope it will be readable to you. Suppose AC1 for area 1, suppose we are writing B1 delta F1 plus delta P tie 1 2, right. So this is area controller. I can take any combination such that at steady state, as long as the integral controller is there, at steady state you will find delta F1 will become 0 and delta P tie 1 2 will become 0. Hence AC1 also will become 0. So that means in general, even if you take this combination, say AC1, I am just putting in my way, AC1, say alpha 1 into say delta F1 I put, plus alpha 2 into delta P tie 1 2 I put, say alpha 1 and alpha 2, alpha 1 and alpha 2 both has to be your greater than your 0, right. And so in that case what will happen, any combination you take, that AC will become 0 at steady state, because you have integral controller, right. But there must be, but question is that on their choice will put some problem, particularly during the transient behavior, right. So that is why we have to have say your what you call some kind of philosophy for proper choice of B1, particularly the frequency bias setting, that B in general, right. So this therefore the AC actually consider the following area control error applicable for a 2 area power system. Suppose we have taken, just now I told, say AC1 as steady state is equal to some constant A1 into delta P tie 1 to steady state plus B1 delta F SS steady state is equal to 0 at steady state. This is equation 45. And AC to steady state A2 into A1 to delta P tie 1 to SS plus B2 delta F SS is equal to 0, right. So in that case what will happen at steady state, your at steady state actually your delta F1 is equal to delta F2 is equal to delta F steady state. This is all steady state, right. That is why delta F SS delta F SS. So at steady state actually delta P tie 1 will become 0 and similarly delta F will become 0, right, for all non-zero values of A1, A2, B1 and B2, right, because you have the integral control action. Therefore AC1 and AC2 their values will be 0 at steady state, right. So however, the composition of area control error signal is more important from dynamic performance consideration, right, because we have to see the transient behavior, that is a dynamic performance. This can be explained by considering the transient response of the AGC system to a sudden increase in the load of area 1. So sudden increase in load will result in decrease in system frequency, because we know that if real power load increases, the frequency falls, right, and if load decreases, then frequency rises, right. So followed by governor response, which limits the maximum frequency excursion and subsequently brings the frequency deviation back to a value determined by the regulation characteristic of both system. And from equation 38 we can write, for example, we will go back to equation 38, right. Here we will go back to equation 38 and 39. Here suppose load disturbance has happened in area 1 and there is no load disturbance in area 2. That means delta PL2 is equal to say 0, right, because there is no load disturbance in area 2. And another thing, that frequency response characteristic, let us define that beta 1 is equal to your B1 is equal to D1 plus 1 upon R1, right. Similarly, you define beta 2 is equal to your B2 is equal to D2 plus 1 upon R2, right. This you define and assume that load disturbance has happened in area 1, but there is no load disturbance in area 2, right. Therefore, you put here delta PL to, and another thing, we assume that area capacity ratio, right, A12 we define by minus sign PR1 upon PR2, you assume they are same, that means we assume PR1 is equal to PR2, right. In that case, your A12 will be is equal to minus 1.0, right. So, all these things you put in this equation, you put A12 is equal to minus 1, delta PL2 is equal to 0, this one you make it beta 1 and this one you make it beta 2 for both the equations. If we do so, now I am cleaning this one, I hope you have understood, I am cleaning this one. So, if you make it, then this equation, actually this equation, it will become that your minus delta PL1, because A12 is equal to minus 1, this is 0, and here A12 minus 1 means this will be plus, and this is beta 1, this is beta 2. So, basically it will be beta 1 plus your beta 2, right. This is your delta F steady state is equal to minus delta F your PL1 upon beta 1 plus beta 2 following a load disturbance. Now, in this case that delta P tie 1 to SS, in this case also same thing, put delta PL to 0 and this is my beta 2, right. So, this can be written as minus beta 2 delta PL1, right, divided by, again this is A1 to minus 1, so it will be plus. So, it is actually beta 1 plus beta 2, right. So, this is minus delta PL1 upon beta 1 plus beta 2, and this is minus beta 2 delta PL1 upon beta 1 plus beta 2, right. So, this is your this expression for steady state error expression for this one frequency, and this is for the tie power deviation, right. So, now we will go back to that equation, right. That is your AC1 is equal to B1 this thing your B1 delta your what to call, this is your delta FSS, similarly for delta P tie, right. So, now we will go back to this equation that your this thing just now I told you that if we put delta PL to 0, put A12 is equal to minus 1, it will be beta 1 plus beta 2. Now, AC1 is equal to say B1 delta F1, right, delta F1 plus your delta P tie 1 2, this is okay, right. Now, at steady state, when you look into the steady state, that means ACE, right, 1 say steady state is equal to B1 delta F steady state, right, plus delta P tie 1 to steady state. Now, B1 is equal to beta 1, this color is red, this is also becoming red, but it is much thick. So, I think it is readable for you, right. So, in this case, if you use beta B1 is equal to your what you call beta 1 and B2 is equal to say beta 2, right, and steady state we have seen the values. So, B1 is equal to beta 1, that means here I am writing for you, that means AC1 steady state is equal to B1 is equal to beta 1, and delta FSS we have seen for a step load disturbance in area 1, area 2 there is no disturbance, and area capacity ratio is same, say A12 is equal to minus 1, because PR1 upon PR2, PR1 is equal to PR2. So, if we substitute here, it will be beta 1, right, then minus delta PL1 divided by beta 1 plus beta 2, this is one equation. Similarly, your delta P tie 1 to SS I showed you before, right, that is equal to your minus beta 2 delta PL1 upon beta 1 plus beta 2, right. So, if it is so, you take your what you call minus delta PL1 common, if you take, so it will be minus delta PL common, numerator will be beta 1 plus beta 2 and here also beta 1 plus beta 2, right. So, that is nothing but minus delta PL1, because this one will be cancelled. That means at steady state, that AC1 SS is nothing but it is coming minus delta PL1. Its meaning is that if there is a your what you call, there is sudden increase of load. So, area 1 will accommodate in own load changes, that means that power will be generated from the generators in area 1, right, and accordingly it will do this. But if you take now using the same philosophy, if you take ACE2, so ACE2 steady state, say directly I am writing ACE2 steady state is equal to B2, then delta F steady state, right, plus A12 delta P tie 12 steady state, right. So, A12 is minus 1. So, this B2 delta F SS, delta F B2 is equal to beta 2. So, here you can make it, this is my beta 2 and delta F SS is minus delta PL1 divided by beta 1 plus beta 2, right, and delta P tie 1 to delta P tie 1 to SS also we have seen before, right. So, A12 is equal to minus 1. So, so I am making it here, this one, hold on, I just hold on, I am writing here that it is beta 2 then minus delta PL1 divided by beta 1 plus beta 2, right, and A12 is minus 1, so minus, and delta P tie 1 to SS we have seen before that minus beta 2 delta PL1 divided by beta 1 plus beta 2, right. So, in that case what is happening, that this is your beta 2, this is also beta 2, this is minus and minus plus. So, what will happen in the numerator will be 0, right. So, that means my ACE2 SS will become 0, right, because this is minus beta 1 beta 2 denominator is common and this is minus minus plus beta 2 PL1 beta 2 PL1 will be cancelled. So, basically it will be 0 upon beta 1 plus beta 2, therefore, steady state error ACE2 SS will be 0. That means, it suggests that whenever there will be a load disturbance in your what you call in area 1 generation should accommodate this load, right, and area 2 in the case of your area 2, this ACE2 steady state is becoming 0. That idea is that if load disturbance happens in area 1, that disturbance which has happened in area 1, it will be completely unobservable by the area 2. This is the meaning of this one, right. So, that is why this is all these things given, but I told you how we have got it, right. So, at this point just there will be deviation of tie power flow from its scheduled value. Supplementary control which is much slower than the primary speed control will now come in responding. Let us now the steady state, let us now study the following case. Now, second case, this already I explained, that AC1 will be steady state will be minus delta PL1, this already I told you, and AC2 SS will completely will become 0, right, this will become 0. These two things already just I derived this, right. So, how the meaning is. So, now from the above we can conclude that only the supplementary control in area 1 will respond to delta PL1 and change generation so as to bring AC1 to 0, that is area control error to 0. The load change in area 1 is thus unobservable to the supplementary control in area 2, right, because AC2 at steady state becoming 0. Now, another case, just for the sake of this understanding, we let us assume another thing, that your beta 2 is equal to B2 is equal to 2 beta 2, A12 is minus 1 and B1 is equal to 2 beta 1, right. So, in that case what will happen, that if you your what you call that use that same thing, that suppose it is given that AC1 SS, you will get this one AC1 SS. So, delta P tie 1 to SS, right, plus this B1 is actually 2 beta 1. So, it is 2 beta 1 delta F SS, right. So, we know delta P tie 1 to SS. So, in A12 area same thing, A12 is equal to minus 1, right. So, this term will be, if I recall correctly, it is minus beta 2 delta PL1 divided by beta 1 plus beta 2, right, and this term plus it is 2 beta 1 and delta FSS already known that it is minus delta PL1 divided by beta 1 plus beta 2, right. So, in the this way your what you call sorry, beta 1 beta 2, it will be actually your b 1 your what you call d 1 plus 1 upon r 1 and your what you call d 2 plus 1 upon r 2. So, if it comes like this, so finally, if you simplify this one, it will be minus delta P L 1, then 1 minus beta 1 minus 1 upon beta 2, right. So, in that case what will happen, just you simplify, one term will come beta 1 plus beta 2 upon beta 1 plus beta 2. I mean, you break this thing, it is minus beta 2 delta P L 1 and beta 1 plus beta 2, and it is plus 2, it is minus plus minus 2 beta 1 delta P L 1 upon beta 1 plus beta 2, right. So, that way you can actually what you just simplify this, then you will get, it will become 1 minus 1 upon your what you call beta 2. Let me do it for you. So, this one actually it is minus beta 2 delta P L 1 divided by beta 1 plus beta 2, right. And this one also you can write separately, minus beta 1 delta P L 1 by beta 1 plus beta 2, right. So, again another term you write minus your beta 1, hope overwriting will be able to understand this beta 1 plus beta 2, this way you write. So, in that case if you write and simplify, right, then you will find that this one actually will become minus delta P L 1, you take common, beta 1 plus beta 2 what you call that your what you call will be cancelled. So, just let me make it here. So, here what will happen, that your minus delta P L 1 you take common. So, you will find beta 1 plus beta 2 upon beta 1 plus beta 2, right. This is one term. Then another one you can write that plus beta 2, right, divided by beta 1 plus beta 2, right, because your beta 1 is equal to your just hold on, that b 1 is equal to 2 beta 1, right, it is okay. So, it will be beta 1 upon beta 1 plus beta 2. So, C 1 S S is equal to your b 1 delta F 1 plus delta p tie 1 2, right, S S. Okay, ठीक है. So, here I am writing again, right. So, AC 1 steady state is equal to B 1 delta F S S plus delta p tie 1 to steady state, right. So, we are taking say B 1 is equal to 2 beta 1. So, if we put here 2 beta 1, so it will be actually 2 beta 1 and delta F S S we know that minus delta P L 1 divided by beta 1 plus beta 2, this is one term, and delta p tie 1 to S S we know minus your beta 2 divided delta P L 1 divided by beta 1 plus beta 2, right. So, this is actually 2 beta 1. So, if you just what you call, now if you simplify this one, this is minus beta 2 delta P L 1. So, this term it can be written as minus I am making it here somewhere here, this term just you 2 beta 1 you make twice, that is beta 1 into minus delta P L 1 upon beta 1 plus beta 2, again you write minus beta 1 into delta P L 1 upon beta 1 plus beta 2, right, and then you take common and you simplify. So, if you do so, then this term will become, this is your beta 1 then your minus delta P L 1 divided by beta 1 plus beta 2, right, this term. Then again another term is there. So, that will be your minus your beta 1 delta P L 1 upon beta 1 plus beta 2 and minus beta 2 delta P L 1 upon beta 1 plus beta 2. So, if you take your minus common, then it will be beta 1 upon beta 1 plus beta 2 upon beta 1 plus beta 2. So, basically it will become actually minus your delta P L 1, right. So, this way it will come. So, if you just take these things your what you call the second term, that you just take common minus delta PL1. So, it will become minus your beta 1 plus beta 2 upon beta 1 plus beta 2, and this is minus your delta P beta 1 upon your what you call beta 1 plus beta 2, this one. Now, further you can simplify this, So, I am just deleting this one, that your, then that means if you take minus delta PL1 common, then it beta 1 upon beta 1 plus beta 2, right, and then that term will be your what you call, that term will be 1, right, if you take your this thing is common. So, after this if you just simplify, right, then let me go back, right, let me go back. So, you will get this term actually your, just hold on, this term, that minus delta PL1 1 minus 1 upon beta 2, just you simplify that one, ultimately you will get that this is minus delta PL1 1 minus 1 upon beta 2, just you put those things, that B1 is equal to 2 beta 1 here, and just simplify, and your A12 is equal to minus 1. So, in that case what will happen, if you put B1 is equal to 2 beta 1, then we have to just hold on, when B1 is equal to 2 beta 1 here, right, in here so, in this two equation, I mean whatever we have made it from here, that your in this expression, just to make it that your B1 is equal to beta 1 is equal to your B1 and beta 2 is equal to B2, right. So, whatever it is, now we are changing it, that we are making it to that your what you call, that your B1 is equal to 2 beta 1 and B2 is equal to 2 beta 2. So, in that, and you just put it and simplify, then you will get this expression, this what you call this this expression, this delta p tie 1 to SS plus B1 delta f SS will be minus delta PL1 then 1 minus 1 upon beta 2. So, if you look into this, then you will see it is not simply minus delta PL1, another term is getting added, right. So, similarly for area 2, right, if you look into that AC to SS will become, if it is minus, because A12 is minus 1 minus delta p tie 1 2 plus 2 beta 2 delta f SS, right. So, in that case it will simply become that your what you call, that you will become minus your delta, just hold on, minus delta PL1 upon beta 2. This means what? That a steady state AC1 also showing some steady state error, and in this case AC2 also showing some steady state error. It is not 0, it is minus delta PL1 upon beta 2, right. That means if we say such kind of thing, in that case B greater than beta, that area 2 your what you call, that your generator also has to respond to generate this amount of power at the steady state. So, that is not desirable. So, best choice for AGC is B is equal to beta. Okay, next we will see that when previous case we saw that when B1 is equal to B2 is equal to your B1 is equal to beta 1 and B2 is equal to beta 2, but in this case we will see that your B1 is equal to 2 beta 1 and B2 is equal to 2 beta 2 and A12 is equal to minus 1. Then if you find out this one, you forget about this thing. If you find out that ACSS is equal to delta p tie 1 to SS plus B1 delta f SS, but B1 is equal to 2 beta 1, here it is, right. So, if you substitute and if you do it like this, then this will actually become that minus delta PL1 divided by B1 plus beta 1 plus beta 2, then into beta 2 plus 2 beta 1, right. So, in this case it is not minus delta PL1 into your beta 2 plus 2 beta 1 upon beta 1 plus beta 2, right. This is your AC1. So, AC1 is not becoming actually minus delta PL1, right. So, next we will go to your next. So, similarly for the next one, that your minus delta p I want to forget about this one, right. So, in this case, your if you substitute all these things, it will actually become, just check from yourself, minus delta p L 1 divided by beta 1 plus beta 2 into your beta 2. So, we can see that on both the cases for AC, in this case AC2 SS is not 0, as when beta B1 is equal to beta 1 and B2 is equal to beta 2, at that time it was AC2 was 0, but in this case it is not. That means what does it signify? Actually it signifies that if you will not say that B is equal to beta, then your generators in area 1 will generate some power. Similarly, area 2 generator also, they will also respond to this, right. So, therefore, the most logical choice for B is equal to your, what you call that, B is equal to beta, right. So, whatever write up is written here, that your that in here both area 1 and area 2 supplementary controls should respond and correct the frequency deviation twice as fast. However, the generation picked up by area 2 will subsequently reflect itself as a component of AC2 and will be backed up again in the steady state. For AGC, more logical choice frequency bias setting will be B is equal to beta, right. And another thing is there, that B also it cannot be less than beta, right. So, that is not desirable. The reason that your, what you call, there is a question to you, that why B cannot be less than beta. That means B1, if you put B1 less than beta 1 and B2 less than beta 2, that is actually not the correct choice. There is some reason. So, this is a question to you, right. So, next we will go to the regarding integral controller of your, what you call, two area system. So, thank you very much. We will be back soon.